All right, let's look now at the concepts of independence and also the multiplication rule. Two events are said to be statistically independent if the probability of one happening is unaffected by the probability of the other, or whether or not the other has occurred. And sometimes we can judge this simply from our knowledge of the events. Take two baseball games, New York playing San Francisco, and we'll consider the probability that New York wins on a particular day. And on the same day, Washington plays Atlanta, and we'll consider the probability that Washington beats Atlanta on that same day. These events are almost certainly independent. It's not going to matter what happens with New York and San Francisco as far as what happens with Washington and Atlanta. Or we can look at past data and judge independence by the actual probabilities. For example, back to the Berkeley admission data, we can look at the question of whether or not admission is independent of department. So the two events we're looking at are applies to a department, and the second event is admitted or rejected. And you can look here and see that it does matter which department you apply to as far as whether you get admitted or rejected. The two events are not independent. The multiplication rule can be applied when events are independent. And it says simply that the probability that both events will happen is the product of their individual unconditional probabilities. For example, suppose New York beats San Francisco on June 1st, and the probability of that is 0.4, and the probability that Washington beats Atlanta on June 1st is 0.5. Since these events are independent, the probability that both New York and Washington will win is 0.5 times 0.4, or 0.2, 20%. The multiplication rule has been prone to misapplication, and the typical error is to assume that there are independent events when they are in fact not. And there was a famous case outlined in a classic statistics text of a criminal case in which the witness, Bass, observed a blonde woman with a ponytail running away from the robbery scene, and she got into a yellow car driven by a black man with a mustache and beard. The prosecutor engaged a probability or a math teacher someplace and came up with these probabilities. Yellow cars are about a 1 in 10 probability. 1 in 4 men have mustaches. 1 in 10 women have ponytails. 1 in 3 women have blonde hair. Probability is 1 in 10 that you'll find a black man with a beard, and 1 in 1,000 that there will be an interracial couple. The prosecutor then multiplied all of these together following the multiplication rule, coming up with a probability of 1 in 12 million. The jury convicted. But are the probabilities independent? No. You can readily see that once you know you have, for example, a woman with a ponytail, or a black man with a beard is a better example. Once you have both of those, it's not a low probability that you're going to have an interracial couple. It's almost guaranteed. If you have a woman with blonde hair and a black man with a beard, that's pretty likely to be an interracial couple. So you cannot say that the probability is extremely low, that on top of those two factors, you're also going to have an interracial couple. The probabilities are not independent of one another. The verdict was appealed and overturned.